Welcome to the first colloquium of the semester that does not talk about CMS.
They were great.
So today we're happy to have Bharat Ratra, our next door neighbor from Kansas State, going to come and talk to us. Bharat got his BA, BS, MS type thing in Indian Institute of Technology. That's a 5-year crazy program. Then he went to Stanford to relax a little bit after the 5 years in India Tech, where he did, I'm ashamed to say, string theory. But then he decided, he came to his senses and moved to do actually cosmology. Got his PhD in Stanford, then he moved to strings of postdocs in Princeton, Caltech, Princeton, MIT. I met him, I think, we overlapped in Princeton for a year. And we came to Kansas together. He went to Kansas State and I came here in last century. Not to be more precise.
Last millennium.
Last millennium. So Bharat is going to talk about dark energy, constant and time variable. I must say that he didn't mention the real elephant in the room. What the hell is this? Nobody knows what dark energy is, but Bharat is going to give us an hour about it. Bharat.
Thank you. Well, thank you for inviting me. It's always nice to come to the big city from a little town. So I do cosmology, and the reason I do cosmology is all to do with great improvements in technology. So these improvements have led to many, many nice, great telescopes out in space and on the ground, and really good detectors that can catch those photons and turn them into electrical signals, and much faster computers that can analyze those signals. And as a consequence of the data that's been collected, especially in the last couple of decades, there's been two really striking results that have been really strongly reinforced. The first one is that we don't know what makes up 95% of the energy budget of the universe at the present time. So we're only familiar with the 5% that's been studied for many, many years. That's basically atoms and electrons and protons and stuff like that. But that makes up a really tiny fraction. And the other striking result, which is probably going to have much more profound consequences, is that cosmological observations are indicating that either relativity or quantum mechanics are incomplete, and possibly both are incomplete and need to be modified. So you've probably all heard that we're doing precision cosmology. So it's kind of useful to go back in time to other epochs in physics where people have felt the same way. And I don't mean to imply that we don't have a standard model of cosmology. I do believe that we have a standard model. We have the skeleton in place. But we've got to put a lot of the flesh and the muscles and the other stuff on. So I'm going back a little over 100 years, maybe 120 years. And this is a quotation from a really famous experimentalist who basically invented the interferometer, and whose experiments with Morley helped Einstein develop the special theory of relativity in some way, even though Einstein never really acknowledges that. So Michelson, I mean, he says a lot of stuff here, but so physics in 1894 is Newton's 3 laws of motion and his inverse square law of gravity and Maxwell's equations. And Michelson says there's nothing much left to do. All we have to do is do precision physics and look for stuff in the 6th place of decimals. And I don't want to leave you with the impression that because I'm a theorist, I'm biased against experimentalists. So I went and looked for another quotation from an equally famous theorist who lent his name to the absolute temperature scale. And you'll notice the main difference between a theorist and an experimentalist, if I can get this to work. So experimentalist has to explain everything in great detail, is much more verbose than a theorist who comes to the point. There's nothing new to be discovered in physics now. All that remains is more and more precise measurement. And this is 1900. And in 1900, Planck comes along and explains the ultraviolet catastrophe and starts developing the theory of black body radiation. And 5 years later, Einstein comes along and basically lays the foundations of quantum mechanics with his explanation of the photoelectric effect and the theory of relativity. And then 10 years after that, in 1916, Einstein comes up with general relativity, and that's basically what we use for cosmology now. So let me back off a little bit and summarize the main contributors to the cosmological energy budget at the present time. So we know that about 5% of the stuff out there is atoms and some charged particles. And this is the stuff we're made up of. It's the stuff that stars are made up of, and planets and blue whales and elephants and all that stuff. And it was first started to get pinned down, the numbers getting pinned down in the 1960s, a couple of decades after the initial work due to Gamow and his graduate student Alpha and postdoc Herman. They were trying to explain the abundances of the light elements, and they realized that these nuclear reactions would leave a background of photons. And through a very inspired guess, they figured that a reasonable photon temperature would be a few Kelvin, or maybe they said like 20 Kelvin or so. And that's the cosmic microwave background. That was discovered by accident by Penzias and Wilson at Bell Labs, and their measurements were interpreted by Dickey Peebles, Roland Wilkinson, and Penzias and Wilson got the Nobel Prize for this discovery. So the 5% has been pinned down much more accurately now with the Kobe measurements and the other microwave background measurements. But even before that, in the 1930s, Zwicky was looking at clusters of galaxies. So clusters are collections of galaxies, and a galaxy is a typical object like the Milky Way. It's got maybe 100 billion or 150 billion stars in it, like the sun, and it's held together by gravity. And in clusters, you can get thousands of these galaxies, and they orbit each other, and they're bound together by gravity. And so Zwicky kind of could measure how fast these galaxies were moving in orbit by using the Doppler effect. And from that, he could get how much mass he would need to produce a gravitational field to create those speeds. And he realized that the mass he needed to create those speeds was much, much greater than the mass he could get by summing together the masses of the stars and the hot gas. And so he ended up discovering dark matter, because the shiny matter could not produce those masses, and so he had to postulate some stuff out there. And he also knew that these clusters had been around for quite a while, and so this dark matter couldn't be moving much, much faster than the stars or the galaxies, and that was a few hundred kilometers a second. And so it was non-relativistic because its speed was much less than the speed of light, and that's also known as cold dark matter. Zwicky did not know this was not made up of atoms. That came much, much later, 30 or 40 years later, after people had pinned down the amount of atomic matter out there. And so about 20% of the non-relativistic, 20% of the energy budget is made up of non-relativistic matter. This stuff is also non-relativistic. And so about 25 to 30% of the stuff out there is non-relativistic or cold matter. And some of it's baryons, most of it's not. More recently, people have discovered something much, much stranger, and they've given it the name energy. And this is not energy in the same way that we mean kinetic energy or potential energy. This is a name, and it's a name for a substance that does something strange. So it's to contrast it with matter. It's been called energy. It's also dark, but it moves much, much faster. And if it's made up of particles, those particles are probably moving at speeds close to the speed of light. And we also know it's not made up of atoms. And it's by far the biggest contributor to the energy budget of the universe now. About 3/4 or somewhere around the 70% of the energy budget is made up of this strange substance. And this was measured in the 1990s in the supernovae observations, for which they got the Nobel Prize a few years ago, Marie Schmidt and Perlmutter. So we basically don't understand 95% of the energy budget of the current energy budget of this model. But we do have a pretty good standard model of cosmology because we can make predictions. And so So I'm really glad Hume's here. He doesn't need to get this bunch line. Usually it's the chairman that needs this, but clearly when 95% of the energy budget is made up of stuff that we don't understand, to have a balanced physics department for every person you have studying atoms, you need 19 cosmologists. So here's the outline of the talk. I'm going to try to motivate dark energy and then look at a couple of models of dark energy. There's the standard model where you have dark energy being a cosmological constant, and then there's cold dark matter. That's the next biggest contributor to the energy budget. Some people want to make this into a dynamical variable, and they model it using a scalar field, which we use the label phi for, and that's phi CDM. And these models are a little bit complex. So there's a parameterization which is called XCDM, where you use a fluid with an equation of state. And it's kind of incomplete, so I'll talk a little bit more about that in a while. But basically, we're going to look at these three models of parameterizations, make predictions, and compare to observations, and then try to constrain the parameters of the model and look at different data sets and see if they suggest the parameters are in the same region of parameter space. And then I'll look a little bit at what happens in the earlier universe when dark matter dominates over dark energy and the universe decelerates. And we're starting to see evidence of that, this transition from decelerating expansion to accelerating expansion. And then if I have time, I'll put in another parameter, which is the curvature of the spatial hypersurfaces, and go and look at some open issues. So the general motivation is that we're doing cosmology, and we only have 3 or 4 or 5 sigma results. So we've got to use a model to interpret these results, because you cannot get model-independent constraints. And your model's got to be motivated a little bit by some of the physics, and you want to have the least number of free parameters so you can get the strongest constraints. So we're going to use models. And the constraints, unfortunately, then are going to be model dependent. And the way you get around this is to use many, many different models and analyze the data sets with these different models and see if they predict the same things as far as the models goes. For instance, do all the data sets predict that the expansion of the universe is accelerating? And if all of them do for all the different models, then you're pretty convinced that that's model independent. And if you're using models, you can combine different data sets and get constraints on the models from different data sets. You can also look for hidden systematic errors, because if one model is pushing you to one part of parameter space and another model pushes you somewhere else with a different data set, then there's probably either a problem with the model or with the data. And with further work, you can figure out which it is. So I'm going to start with some really basic facts. So we know that the universe expands, and this is a really difficult thing to get a handle on. So we know that on large scales that there are two important forces. There's the electromagnetic force, which is an inverse square law force, and you're familiar with Coulomb's law. And there's also the gravitational force. And the electromagnetic force is much, much stronger than the gravitational force. So if you take two protons and ask what the electromagnetic repulsion is compared to the gravitational attraction, you'll find that the electromagnetic repulsion is 36 orders of magnitude stronger. But when you take matter and start piling it on and go from small atoms to planets to stars to bigger objects like galaxies, you end up making everything basically charge neutral. You have an equal number of electrons and protons, so the electromagnetic forces cancel out, because like charges repel and unlike charges attract, and so that cancels out. And then gravity wins. So for bigger objects like galaxies or clusters of galaxies, gravity is more important, and it's the dominant force. And gravity is described by Einstein's theory of general relativity, and probably for our purposes, the main interesting thing about that is that he made space and time dynamical. So space also evolves, and time also evolves, and that's part of the dynamics of the model. So as you go along and space is evolving, it kind of produces more of itself in regions where there's not much mass, and it takes the mass along for the ride. So that's what pushes galaxies apart. It's a space creation between the galaxies. And that's the process that leads us to be able to study these models. Because if you have a wave propagating in a space that's expanding, and here's a cartoon, So I have a universe. It's a one-dimensional universe. It's the circumference of the circle. And I've drawn it at one instant of time, and then I've drawn it again at a later instant of time. And the size of the universe is 2 pi times this function a of t, which is the radius, and I'm going to call this the scale factor. So as time goes on, the circumference gets bigger because the scale factor is getting bigger. And if I have a wave on this universe and it has a wavelength lambda over here, it has a certain number of zero crossings. And if there's a big separation in the oscillation period of this wave, and the time scale on which this universe doubles in size, there's a separation in the energy scales also. And you can't put energy into the wave from the expansion, or you can't take energy out of the wave and put it into the expansion. So the only option you have is the number of zero crossings of this wave have to remain the same as the universe gets bigger and bigger. And that can only happen if the wavelength gets bigger. So if you start out with blue light over here and eventually go long enough, the light turns red. And the ratio of the two wavelengths is going to be in proportion to the scale factor. And so that's what Slipher saw when he was looking through his telescope at external galaxies. He saw a whole bunch of them moving away from us because he could see this Doppler shifting, and he saw most of them had redshifts. And this was in 1912, and he didn't really know what to make of it because there were two options. He could have said that the universe started out in this explosion at one instant of time at one point in space, and everything moved outwards. But that would have been the wrong explanation, and it's a little bit difficult to understand what's happening without a few more details. So the next important detail came in 1929 when Hubble started measuring distances to these galaxies that Slipher had measured redshifts for. And Hubble measured distances by finding Cepheid variable stars in these galaxies, and he used Henrietta Leavitt's period luminosity relationship to get the wattage of those stars, and then he used the inverse square law to get the distance from the wattage. And what he discovered is this really, really nice equation here. And in words, it's up here. The further apart the galaxies, the greater the redshift and the faster they separate. So if you look at a galaxy at a distance r from us, it's moving away from us at a speed v. If you double that distance, it's moving twice as fast. If you triple the distance, it's moving 3 times as fast. And this constant of proportionality is the Hubble constant. And it's got somewhat strange units because of the way astronomers measure things. So they measure velocities in kilometers a second and distances in megaparsecs. And so it has units of kilometers per second per megaparsec, where it's really just inverse seconds because the kilometers and megaparsecs are both distances. But in these conventions, this is my favorite range for the Hubble constant. This is the 1 sigma error bars. So this is what Hubble found, and here's some of the data. So I've plotted velocities over here and distances over here, and we have residuals here. We can forget about it. So if we look at a galaxy about 100 megaparsecs from us, it's moving away at about 7,000 kilometers a second. A galaxy, well, I guess the battery is dying on this, so probably better transition to this. A galaxy 200 megaparsecs from us is moving away at about 14,000 kilometers a second. And this is the Hubble law, the straight line. It's the best fit to this data. This is a little older data. My favorite value is around 68 now. And we've been doing median statistics analysis of a lot of the Hubble constant measurements. And it's kind of been around 68 for maybe a decade and a half, and it's kind of really nice that the microwave background measurements, both from WMAP and Planck, come in around 68 or 67, and also a lot of the BAO oscillation, baryon acoustic oscillation measurements give you this Hubble constant. The local measurements of the Hubble constant, when you go back to using Cepheids and supernovae, tend to be a little bit higher. And that's kind of a really interesting puzzle, because if you look at a lot of this data and allow the Hubble constant to vary, so the local measurements are favoring something around 74 kilometers per second per megaparsec, while all the larger scale ones like the microwave background and BAO come in around 68. You do a analysis of a bunch of data. So there's microwave background on large angular scales, much smaller angular scales, and galaxy clustering data, and allow the Hubble constant to be a free parameter and parameterize the number of light neutrino species. And you find that if you go with the local measurements of the Hubble constant, you need about 4 light neutrino species, while the standard model of particle physics is much, much happier with 3. Depending on how they decouple, it's a little bit more than 3. So if you go down to about 68, that's quite consistent with the standard model of particle physics. So it's kind of remarkable that the standard model of particle physics favors the Hubble constant of 68 over 74, when if you think back 20 years ago, we didn't know the Hubble constant to a factor of 2. So this is a really interesting result, and things are going to get much more interesting when the precision of the experiments improve. So we have an expanding universe, and because it's expanding, and you can have observers that are at rest with respect to this expansion that are moving with it, or you can put observers on rocket ships, and if you put them on rocket ships, they're going to see a somewhat different picture of the universe than those at rest with respect to the expansion. So we have to be a little bit careful and phrase everything in terms of these observers, which we call cosmological observers, who are at rest with respect to the expansion. And these observers are going to see that the universe is isotropic. And so we introduce what's known as the cosmological principle and postulate that all such observers are going to see that the universe is isotropic on large scales. And if you have something isotropic for all observers, that means it's got to be homogeneous. So this is some more jargon. If something's isotropic, you're standing at one point and you're looking around you in all directions and it looks exactly the same. But if you translate yourself in space and it looks isotropic to you again, then that means it's homogeneous. And the easy way to think about homogeneity is to think about the inside of a gallon jug of milk. No matter where you translate yourself in space in that gallon jug, it looks the same, it looks white. And that has much, much more symmetry than just a model that's isotropic about one observer. And so it simplifies cosmology a lot. And if we ignore global topology, which we can't really discuss with current equations of motion or physics from general relativity, we're just left with 3 possibilities if you want a homogeneous universe. And for those of you who know GR, I've put the line element up here. The scale factor shows up over here. Again, this is for the evolution in time. This is the scale factor for the spatial geometry. And these are the 3 possibilities. I've suppressed one spatial dimension. So we could live on the surface of a sphere, and the scale factor could be, you could think of it in terms of the radius of the sphere, but there's nothing inside, there's nothing outside. The sphere just keeps expanding. You're a little ant, and you can walk around on the surface, and distances between the points get bigger and bigger as it expands. And this is called a closed universe, and its spatial curvature is positive. You could also have an open universe, and that's the saddle shape. And again, this will expand, and the distances between points gets larger and larger. And it can't have any edges. It's got to go out to infinity, because if it did have an edge and you went to it and you looked outside, it would look different than when you looked inside, so it wouldn't be isotropic. And that's an open universe, negative space curvature. And this is a flat universe. Again, it can't have any edges. It's got to go out to infinity in both dimensions. And this has got 0 space curvature. I've also introduced this parameter here, this omega sub 0, which is the density of matter in these universes in a strange system of units. I'll come back to that later. But this is an overdense universe, this is an underdense universe, and this is a universe of critical density. So a universe of critical density has 0 space curvature. An underdense universe has negative space curvature, and an overdense universe has positive space curvature. And I haven't included dark energy here. It gets a little bit more complicated with dark energy. So one major part of cosmology is to figure out what happens with that scale factor as a function of time. And so we need equations of motion. And these guys come from general relativity, and it's a bit messy to write down the full equations of motion. So I'm going to write them down for a really simple model where the mass is modeled as a fluid. It's an ideal fluid, and it's got an equation of state, and that's has a gravitational field associated with that that leads to the expansion of space. So we get an equation, and the easiest way to think of this equation is to think of an energy conservation equation. So this tells you the expansion rate of the universe. The dot is the time derivative, a is the scale factor. So the expansion rate squared is determined by the various terms on the right-hand side. And gravity is really important. That's why there's a big G from Newton's law of gravity. This Newton's gravitational constant. And rho is the mass density or the energy density of this fluid, because we don't want to deal with the whole universe. The whole universe could be infinite, and then you'd be talking about an infinite mass. So we take a little volume of the universe and write down the equations of motion for that little volume, and the thing driving that would be the mass per unit volume. The curvature of the spatial hypersurfaces can contribute, and so that's that term. And we could have a cosmological constant. So if you know how this guy evolves in time, you can plug this into your computer and integrate, and you'll know how A changes with time, how the universe gets bigger and bigger as a function of time. But we don't know how this guy evolves in time. So we've got to get an equation that determines that, and that equation comes from energy conservation for the fluid. And it says that the time derivative of the fluid is determined by the fluid energy density and the fluid pressure. And to complete this set of equations, you have an equation of state for the fluid. And so you solve these guys numerically or analytically, and you can predict what goes on. So we know that this function h of t, and the present value is the Hubble constant, but h is just the expansion rate divided by a. And we know this is positive because galaxies are redshifted from us. So the next obvious question, being physicists, is what happens if you differentiate this once more with time? And do you know whether this rate, this expansion rate, whether it's increasing or decreasing with time? And the easy way to see this is to take this equation and differentiate it and use these other equations and do a little bit of calculus and get an acceleration equation. And here's the acceleration equation. This is a lot like a is equal to f over m. So we have the acceleration here. It's the second time derivative of the scale factor. And the force that's driving that acceleration is over here. This is a g because it's gravity. And we have the mass density, and we have a strange contribution from pressure. And if I wasn't working in natural units and I put back the speed of light, there would be a c squared in the denominator of this term. So that's telling you that this is a relativistic effect. And for those of you who've done a little bit of relativity, you'll notice that this is the active gravitational mass density. So let's first just ignore this guy for a second and work with this equation with just the rho. So the pressure is measuring the kinetic energy of your galaxies, basically. So let's put them at rest and let them go with the expansion so they don't have their own velocities relative to the expansion. Then the acceleration is going to be negative because rho is mass per unit volume, and you don't have a choice. So what this is telling us is that if you have a bunch of galaxies out there, and Einstein comes along and says, I'm going to create space between these galaxies and I'm going to push them apart, then the galaxy is also going to pull back on each other with Newton's inverse square law. And this says if the mass is large enough, then the galaxies are going to win, and that expansion is going to eventually decelerate. So the universe will expand, and it'll slow down, and it'll slow down, and slow down, and eventually stop. So let's add back this pressure term. So this is really pressure. It's not a pressure gradient, and it's a measure of the kinetic energy of the substances you're looking at. And you're familiar with this if you ever pumped up a bike tire and felt the barrel of the pump. Because when you pump up a bike tire, you're taking more and more air molecules and pushing them into the tire, and they're banging into each other, and their kinetic energy is going up, and so the temperature is going up, and because of the ideal gas law, the pressure is going up. And so you feel the barrel of the pump gets hotter and hotter and hotter. And that's what's measuring the kinetic energy of these galaxies if they're moving around. This is the rest mass energy, essentially. This is the kinetic energy. And so it's very, very reasonable if you have an additional contribution to the energy of the system, then you know that m is equal to E over c squared. So there's a mass associated with that. And then because there's a mass, it's going to gravitate. And so moving galaxies also contribute, and they slow down the expansion even more because rho plus 3p is bigger than just rho. so you have this really, really nice result. You predict that the expansion of the universe is going to be decelerating. So you go tell your observer friends to go out and measure this, and they do, and they measure it, and they find that A double dot is actually positive. So you're in trouble because of this minus sign. So we can't flip the sign of rho because there's no such thing as negative mass. And so your only hope is that you have a way of making negative pressure. And it turns out that in the lab we're aware of some substances where you can have negative pressure. And an example of that is the Casimir effect, where you take two metal plates and you change the boundary conditions of your quantum mechanical system, and you see that that behaves as though there's a negative pressure. You also see this in the Lamb shift when you look at the hydrogen atom and you account for the effect of the nucleus on the electron. So we're aware of these systems in the lab, and a system on cosmological scales where you have a large negative pressure that overwhelms rho and makes rho plus 3p negative is called dark energy. So that's all it is. It's basically a substance with rho plus 3p negative. And so that way we can reconcile Einstein's equations with the accelerated expansion of the universe. The other option, of course, is that this equation is wrong and general relativity is the thing that needs to be corrected. But we have quite a bit of evidence that this equation is good, and that's what I prefer going with, and postulating a strange substance instead of saying GR is wrong. So this parameter omega I'd introduced earlier is just the ratio of whatever rho you have to this critical energy density, which is given in these units here in grams per cubic centimeter. And this is the energy density you get if you set this to 0, set this to 0, put the measured value of the Hubble constant here, and then you just have an energy density. And that model is called the Einstein-de Sitter model. It's the simplest cosmological model, and it's useful to measure everything relative to the Einstein-de Sitter energy density because you don't want to be carrying around so many powers of 10. It makes it really messy to write things out. Okay, so dark energy is a little more complex to get a handle on, at least as far as the observations go. So what I'm going to do is I'm going to compare two universes, a slowly expanding universe and a more rapidly expanding universe. And I'm showing you Hubble's law in both of these guys. So if you go out a certain distance d and look at the galaxy at the same distance in these two universes, the galaxy in the slowly expanding universe is going to be moving away from you slower than the galaxy in the more rapidly expanding universe. And as you go to larger and larger d, it takes longer and longer for that light to reach you. So when you look at a galaxy further away, you're seeing it at an earlier time. So what we want to try to do is figure out what our universe does. So there's three possibilities: that the expansion rate of our universe is constant, like this purple line, or it could be that when you go to really large distances way back in the past, the universe expanded more slowly in the past, like the blue line, and as it came to the present, it kind of approached the purple line from above. So this would be an accelerating universe, or it could be that in the past it expanded more rapidly and the expansion slowed down as you came to the present. This would be a decelerating universe. So you want to try to go out really, really far back in the past. And what you do for that is to look for really, really bright objects. And in the 1990s, the objects for which you could do this were the type 1a supernovae that were occasionally as bright as a whole galaxy with 100 billion or 200 billion stars. And they could be as bright as this galaxy for maybe a couple of weeks. So you can see them really far away. And people did that, and they found that everything was on the blue side, so that the expansion of the universe was actually accelerating. So it expanded more slowly in the past, and as it came to the present, it sped up. So that's the evidence for dark energy, and I'm sure a lot of you have seen plots like this, where you look at the density parameter of dark energy and the density of ordinary matter. And if there was no dark energy, you'd lie on this line at 0. But the supernovae kind of force you up here to a region of parameter space where you have non-zero dark energy, and that's about 3 or 4 or 5 sigma away from zero dark energy. So it's not a terribly strong result as far as particle physics goes, but it's strong enough to give the Nobel Prize for cosmology. So what do we know about dark energy? We know it's the major contributor to the energy budget now, and I think that's pretty secure. So is it just Einstein's cosmological constant, or does it weakly vary in space and in time? And to answer questions like this, we're making a bunch of assumptions. We're assuming that the general theory of relativity is correct, and the astronomers have got rid of all their systematic errors or beaten them down enough. And one way to deal with this is to look at a bunch of different models where you allow dark energy to vary in time, and then compare the predictions of those models to observations. So I'll start out with the standard model, which is lambda CDM, and I'm going to show you on a log-log plot the energy densities as a function of time. So we live over here. This is log of the scale factor, and the scale factor is a monotonic function of time. So we live here, and as you go back to the early universe. But I'm not going to go back that early. I'm not going to go into the radiation-dominated epoch, so I'll just go back into the matter-dominated epoch and then the dark energy-dominated epoch. So here's the Einstein-Friedman equation. There's non-relativistic matter, and that has an equation of state such that it's dominated by its rest mass energy. So if you want its density, its mass per unit volume. The volume expands in 3 dimensions. Each dimension has the power of the scale factor, so you get a 1 over a cubed in the denominator, and that's the blue line. So when this guy dominates, rho plus 3p is greater than 0, so you have a decelerating universe, a decelerating expansion. Then space curvature kicks in. That's the orange line. It's 1 over a squared. And then you can have a cosmological constant, and that's this horizontal line because it doesn't vary with time. And so by the time you get over here, rho plus 3p is negative, and the expansion accelerates. So you go from decelerating expansion to accelerating expansion. So this a sum rule. I mean, you naively think there are 3 parameters that are needed to specify this model, but actually you only need 2 parameters, and that'll become clearer in a little while. And conventionally, these 2 parameters are the energy density of the non-relativistic matter at the present epoch in those strange Einstein de Sitter units, and the energy density in the cosmological constant, which doesn't change with time. And you can see the problem that everybody has with this. So this guy is an energy density, and if you go to natural units and take the 4th root, that's an energy scale. And the energy scale set by the supernovae observations is a few millielectron volts. And this is very, very disturbing to a lot of particle physicists, probably because millielectron volts is the scale of chemistry. And so we don't want to introduce a new fundamental scale at that energy scale in the universe. I mean, recently people have been discovering neutrino masses at a millielectron volt, and maybe this has something to do with the dark energy, but I haven't seen a really convincing model tying these together. So the next model we want to look at, so what you can do if you go back to this lambda CDM model, so the problem is it's a millielectron volt now, and you don't want to introduce a new fundamental scale of a millielectron volt. So you take this line and you tilt it, and you go back 13 or 14 or 15 billion years, and at that point it's way, way, way higher here, and instead of a millielectron volt, it might be 10 to the 15 GeV, and that's your new energy scale that describes dark energy. And that you can tie in with a gut model or an inflation model, and you no longer have to introduce a new scale of a millielectron volt. So one way to do that is to take this energy density and tilt it up, and I'm going to tilt it up by using an X fluid, and that's a fluid with an equation of state of this form. P, the pressure, is proportional to the energy density, but this equation of state parameter is going to be minus 1/3 or less. And so there's 2 contributions to the Friedman equation here. So one from non-relativistic matter, one from this X fluid. And to make life simple, I've set these to be spatially flat models. So I have dark matter and baryonic matter. As time goes on, the expansion decelerates, then the X fluid kicks in. And if you choose this range, it makes it accelerate and be consistent with the supernovae observations. So conventionally, the parameters that I use to describe this model or parameterize it are the energy density in ordinary matter and dark matter now, and the equation of state parameter for this X fluid. And you can immediately see the problem here with this, because if you slightly perturb this X fluid, it's got a negative pressure, and it's going to collapse, and it's going to collapse very, very rapidly, and it's going to end up with a bunch of black holes, and it's not going to look anything like the approximately homogeneous and isotropic universe we have. So what you want to do is you want to have something stable that is also negative pressure. And the way you can do that is to introduce a Klein-Gordon scalar field with a strange potential. So I've got the phi CDM model. Again, I'm going to make it spatially flat. And here's the Einstein-Friedmann equation again. So you have ordinary matter, that's the blue line. Down to here, the expansion decelerates. Then the scalar field energy density kicks in, and you can choose the potential energy of the scalar field to ensure that it accelerates there. And the scalar field potential energy is over here. There's a time derivative, a dot here. This is the kinetic energy of the scalar field. I've chosen a very strange potential energy, and I'll tell you why in a second. And this parameter alpha parameterizes the potential energy. So the parameters of this model are the energy density in non-relativistic and ordinary matter now, and the parameter of the potential alpha. This potential has been chosen because when you solve these equations, you can solve them analytically if you're well into each epoch, or if you want to do a transition, then you have to solve them numerically. But you find for a potential of this form where alpha is positive, that there's an attractor solution, and the slope in the scalar field energy density always wants to evolve so as to come over the dominant energy density. So you start this guy out in the matter-dominated epoch, and it always wants to overwhelm the matter energy density. If you do this in the radiation epoch, it does the same thing there. And so this attractor solution makes it extremely stable, and it makes it want to dominate, and it helps resolve partially the fine-tuning problem of the cosmological constant, because it wants to push it down here, and it helps with the coincidence problem too. So what I want to do with these models is make predictions and compare to some observations. So I'll choose a bunch of data that's out there. There's a lot more, but this is just for illustrative purposes. So we'll use the type 1a supernovae data that led to the discovery of the dark energy, the latest versions of these data sets. And we'll look at baryon acoustic oscillations, and we'll measure the Hubble parameters as a function of redshift, and we'll measure how inhomogeneities develop as a function of redshift. So we're going to just look at these models, and I'll kind of illustrate the procedure in the lambda CDM model for one of these data sets. So we want to compute parameters that observations that can be compared to observations. So we want to rewrite everything in terms of the redshift, which is defined this way. The redshift is z, and 1 plus z is just the wavelength you observe compared to the wavelength at the object when it emitted it. So this is the lab wavelength. This is the wavelength after redshifting. And so you can rewrite the Friedmann equation in this form for the lambda CDM model. So you have the contribution for matter. This is the 1 over a cubed term. And if you rephrase it, so you can get the ratio here because of the ratios of the scale factor. And you can rephrase it in terms of the redshift. And instead of 1 over a cubed, you get 1 plus z cubed. The space curvature term, instead of 1 over a squared, it becomes 1 plus z squared. And the cosmological constant term has no dependence on z because it's a constant. And so this is defined, this function here is defined to be the stuff in the square parentheses. And so you can immediately see the sum rule. You just evaluate the Hubble parameter at the present time, and that's going to be canceling out with that. That's going to be 1. At the present time, z is 0, so this goes away, that goes away. And so you end up with 1 equal to omega matter naught, omega curvature naught, plus omega lambda. So there's this one sum rule that constrains the parameters. So there's only 2 free parameters. And conventionally in this model, these are taken to be this guy and this guy. So you can predict the Hubble parameter as a function of redshift. So it depends on the redshift, it depends on your cosmological parameters, and it depends on your nuisance parameter, which is the Hubble constant. So you make these predictions and you compare to the observations, and you can do a chi-squared fit, or you can do a maximum likelihood fit, or whatever you want, and then you get constraints on these parameters. So in this case, you'll constrain these two parameters, and I'll show you a bunch of constraints for a lot of these models. So I'm going to show you a lot of plots like this in the remaining 15 minutes. So there's going to be the lambda CDM plot, the X CDM plot, and the phi CDM plot. The x-axes are always going to be omega matter at the present epoch. The y-axis are going to be the dark energy parameter. So in lambda CDM, it's omega lambda. In XCDM, it's small omega sub x, the equation of state parameter. And in phi CDM, it's going to be the alpha parameter and the potential. So this is for the type 1a supernovae data. So we're looking at about 580 type 1a supernovae, apparent magnitude versus redshift measurements. And there's a bunch of special lines on these plots. So on this dashed line here with the big dashes, that's where the flat models lie. So if you go to omega matter of about 0.3 and omega lambda of 0.7, they add to 1, so omega curvature has to be 0. Omega matter of 0.4, omega lambda of 0.6, they add to 1. So there's no curvature here. Models that lie above this accelerate, models that lie below this decelerate. Here, it's a spatially flat model, but the dark energy is constant if omega sub x is equal to -1. So the models that lie along here are identical to the models that lie along here. And the models that lie along here at alpha equal to 0 are the same as these models and are the same as these models. So we're going away from this favored model, which is a spatially flat one, in 3 different ways. You can go with space curvature and a constant cosmological constant this way, or you can go with dynamical dark energy this way or this way. So all these data sets for these 3 models, the favored model is right over here. It's always omega matter of about 0.3, omega lambda of 0.7, omega matter of 0.3, omega lambda of 0.7, omega matter of 0.3, omega lambda of 0.7. So the standard model is very, very consistent with this data. This is 1 sigma, 2 sigma, 3 sigma. So there's a lot of space for non-flat models and a lot of space for dynamical dark energy models. So you can see this with all these data sets. If we look at baryon acoustic oscillations, the standard model omega matter of 0.3, omega lambda of 0.7 is well within the 1 sigma error bars. And the same is true here, and the same is true here. So there's still a lot of space for non-zero curvature or dynamical dark energy. But the really important thing is that these contours...
Is that 68% confidence coverage? Or
yeah, well, 1 sigma, 2 sigma, 3 sigma.
They're different numbers in two dimensions.
Right. I mean, so that's how we define it, by integrating it over. It's basically 68, 95, and so on. So the contours are rotating. So if you look at the supernovae, they're this way. If you look at the baryon acoustic oscillations, they're that way. And we can look at the other data sets too. So this is the Hubble parameter data set. And I told you for the Hubble parameter, the Hubble constant is a nuisance parameter. So we marginalize over it with Gaussian prior. So you can either use the large-scale ones from the CMB, or you can use the local measurements. Those are the dashed dotted lines. So they shift things by about half a sigma, depending on which Hubble constant you use. But in all cases, omega matter of 0.3, omega lambda of 0.7 is well within the 1 sigma error bars of this data. And you have a lot of room for non-flat models, a lot of room for dynamical dark energy. And these things are as tight as the type 1a supernovae. So that's kind of interesting. And this is the growth factor of inhomogeneity as a function of time. So again, omega matter of 0.3, omega lambda of 0.7 fit the data really well, no matter what model you use to analyze the data. So the standard model does really well. So the first really important thing is that there are large parts of parameter space that are the same, that are favored by all these data sets. So the different data are not inconsistent, and the individual data sets are all consistent with a spatially flat lambda CDM model with omega lambda of 0.7, omega matter of 0.3. But they do not rule out time-evolving dark energy or space curvature. So the next obvious thing is to do this two at a time, and you can keep going on. So I'll just be fast here. The main difference is that the parameter space now is much, much smaller. So this is supernovae and baryon acoustic oscillations. But again, omega matter of 0.3, omega lambda of 0.7 fits the data really well. And if you do this for all the data sets, you see similar sort of plots. This is the Hubble parameter in BAO. The Hubble parameter has the Hubble constant as a nuisance parameter. It moves things around a little bit by half a sigma. But omega matter of 0.3, omega lambda of 0.7, roughly is consistent at 1 sigma with both the Hubble parameter, Hubble constant values. And it doesn't matter what model you use. This is BAO and growth factor, again 0.3, 0.7, fits the data really well. And we can do this with a lot of data sets, so I'm not going to bore you. But so the conclusions are, if you do it two at a time, you get tighter constraints. And the standard model is very, very consistent with this. And you can still have weakly evolving, time-evolving dark energy or some mild space curvature. I'm not going to do this at 3 at a time, 4 at a time, 5 at a time because of the systematic effects. I'm not sure it's really justified to do that. People have done this, and in the series of papers, these guys claim that time-evolving dark energy is favored at 4 sigma over the standard model. But I think the interesting stuff is down here. So there's many different type 1A supernovae data sets. There's about half a dozen of them. And if you use them and do this analysis with each one, the contours move by half sigma. We've seen that the Hubble constant measurements move the contours by half sigma. In some cases, for some of the tests, the density in baryons move the contours by half sigma. So there's a lot of systematic effects, and these guys are going to get dealt with pretty soon, probably in the next decade or so, because we're going to have much, much better data and a much better handle on these. And we'll know the answer maybe in a decade. So there's a couple of other interesting things. So as I mentioned earlier, that at the present time, dark energy dominates and the expansion accelerates, while at earlier times, dark matter dominated and the expansion decelerated. And you can actually see this in the data now. So I'm looking at the Hubble parameter as a function of redshift. This is the present epoch as you go back in time. And these are all the measurements that are available. And I mean, you don't really see this. I'll show this to you in a cleaner plot in a second. But there are these 6 different dark energy models here. And you can see them all decelerate at earlier times and then accelerate. And these are the best fit models to this data set of 28 points. This model and this model are 3 sigma deviant from the best fit models. And they are not consistent with the data at 3 sigma. We can bin this data for more clarity. And you'll see this is pretty clear here, as long as you don't do this at high redshift where you don't have enough data points. But at lower redshift, you can see the transition from dark matter-dominated deceleration to dark energy-dominated acceleration. And you see that in the Friedman equation. But I'm running out of time, so I won't talk about this now. People can ask me at the end. But you can measure the transition redshift, and the transition redshift is about 0.75. When the universe was roughly about half as old as it is now. That's when dark energy took over from dark matter. You can use this data for other things also. If you marginalize over all parameters in each of the models we looked at, you can measure the Hubble constant from the Hubble parameter data. And it's always around 68 or so, 67, which is consistent with the microwave background. It's consistent with the results from WMAP, from Planck, from baryon acoustic oscillations. And it's closer to what we got from median statistics than local measurements of the Hubble constant. And it's kind of unclear why there's this big difference, which is pretty significant now. It's almost 3 sigma. So I guess maybe I should skip this part. I was going to talk about space curvature, but I'm running out of time, so I'll skip that and move on to the end. So there's a whole bunch of stuff out there. We know there's dark energy out there, but we don't yet know if it's a cosmological constant or whether it varies weakly in space and in time. I think the theory of general relativity is correct, and the simpler thing to reconcile this with the data is to add something to the right-hand side of Einstein's equations rather than messing with the left-hand side. And I think the astronomers have done a really great job. They've got a good handle on their systematic errors, and these effects are not going to go away. All the models I've shown you for dark energy only couple it gravitationally to everything else, but in principle it could couple directly, for instance, to dark matter, and that would change things a lot. People have started looking at these models. For the dark matter, we're aware of two particles that are out there that act like dark matter. These are at least the two massive neutrino species that we know are out there, but they don't contribute enough. And so there's got to be a lot of other particles out there that contribute. And it could be one species, and more likely it's going to be a whole bunch of different species, because there's no reason that the 20% of the energy budget that's dark matter is going to be made up of just 2 or 3 things, when the visible part, which is 5%, is made up of many, many more different things. We don't know what kind of theory can be consistent with the observations right now. Supersymmetry seems to be pressed a little bit, at least the minimal models. Maybe it's axions. We might find out from these experiments at CERN at the Large Hadron Collider, or for the laboratory searches in the deep underground mines. There might be some evidence from dwarf galaxy abundances and profiles in galactic nuclei and clusters that the pure CDM model doesn't work, and maybe one way to deal with this is to couple dark matter to dark energy, but it's kind of unclear. So for those of you who thought cosmology was over, I'll just leave this up for 30 seconds if you had some spare time. And these are a few open problems in cosmology after you figured out dark energy and dark matter. And maybe, because I'm running out of time, I can put this back up later. I think I'll just stop here.
Questions?
So this discrepancy in the Hubble constants between the local measurements and the cosmological distance measurements, I mean, the Hubble constant is the measurement of the expansion rate locally, right? So it kind of seems that you want to measure that locally as soon as you get out, as long as you get out of the Hubble flow.
Right.
So it seems odd that you would default to want to use the ones that are measured in Z of 1,000.
Well, they're much cleaner, right? And they're not Z of 1,000. I mean,
microwave background.
Right, microwave background is that high, but baryon acoustic oscillations, I mean, I guess in some ways you're making a model and bringing it down, but the Hubble parameter measurements are Z of 0.5, 1, 1.5. And I mean, the thing that I think is kind of striking is whether you do it with the microwave background or you do it with baryon acoustic oscillations, you do it with the Hubble parameter. They're all coming in around 67 or 68. And I don't know if that means that there's something wrong with the cosmological model, or whether there's some kind of systematic effect in the local measurements, which depend a lot on astrophysics. So you have the Cepheid period luminosity relationship, and maybe you can't push it that much as it's being pushed, but I don't know. I mean, what do you think?
Oh, I don't know. I mean, the understanding of it, yes, it's astrophysics locally, but the understanding of the astrophysics is much better at some level. I mean, compared to supernova. Supernova, we have no idea what causes it. It's a purely empirical model.
Right.
But Cepheids, we know very well how to model Cepheids, and we can now use infrared to get around dust complication.
Yeah.
So there's lots of cross checks. There's like masers with Cepheids in them and type 1A. So
right.
That's why I'm kind of confused with this discrepancy about not an expert on the distance.
Right. Yeah, it just seems to me that like almost all the other measurements using like CMB and baryon acoustic oscillations and HZ are all coming in higher. lower than the local measurements. So I don't know. I mean, I'm not sure what to say.
Yeah,
But I mean, we don't do precision.
Historically, it was always like that. Cosmological, even when it was 150, it was always like that. Cosmology said low Hubble
completely different
constant.
reasons.
And one thing that you can think of is just say that we live in a bubble. So locally, we expand faster than globally. Yeah, right.
Could you explain to a particle physicist what a cosmologist means by the effective number of neutrinos?
It's so if you just go to the standard model, there's 3 neutrinos, right? And depending on how they decouple, they affect things slightly differently in the expansion rate. So you could postulate a sterile neutrino that doesn't show up because it's too heavy, doesn't show up in the Z, for instance, or something. And that is going to affect the expansion rate at very early times. And so that's the way people...
There's some kind of, that's related to the sum of masses or something.
It's not. So the sum of the masses you get from, if it couples the same way, right, to baryons. And so the reason you get that bound from cosmology is because it prevents structure formation, because it behaves like a relativistic fluid, and it couples also to the baryons and washes out structure. And you could postulate things that don't couple that way, but that behave like neutrinos. And it doesn't have to be a neutrino, it could be some other species of some particle that's relativistic at earlier times. So people, that's you need to introduce that if you want the higher Hubble constant value to be correct with the rest of the data.
Greg?
The pure cluster abundances, are they constrain omega matter, just number of clusters, mass function of galaxy clusters?
They constrain, it depends how you do it as a function of redshift. So they end up constraining both omega matter and omega lambda, and it depends on the redshift range over which you do it, what the parameter is that it constrains.
So are those yet competitive with these other techniques? Or?
So they are not as competitive as, they're probably starting to get down to supernovae right now. So the best ones right now are microwave background, baryon acoustic oscillations, and then probably the supernovae and HZ. And the cluster abundances are a little bit weaker than that.
Wait.
I have an ignorant question. That you said in the very beginning that the dark energy is relativistic.
Yeah.
Why?
Okay. It's relativistic because, so let's look at a cluster. So if a dark energy clustered on those scales, so if it had enough mass so that the cluster gravitational field could capture it, then when you're looking at galaxies moving around in the cluster, you'd see the gravitational effects of that dark energy there. And you don't see that. So that dark energy can't be clustered on that scale. It's got to be really smooth. And you can look at larger scales and do the same experiment, and you find that it's really smooth. So it's got to have some pressure that's resisting gravity and not allowing it to collapse down on those scales. And if you translate that into an effective mass for the guy, or well, the way you do it, you translate that into a speed, because the pressure is basically kinetic energy, and that speed is approaching the speed of light.
Quick question. Does Big Bang theory or Big Bang model imply there's actually a center for the universe?
No. So this is really difficult to get a handle on, but what it implies is that every point in space is moving away from every other point in space, and this started happening at one instant of time. So it implies that there's an initial instant of time, and at that time space was probably infinite, and every point in space is moving away from every other point in space.
So it did not start from just the singularity.
The singularity is in time, it's not in space.
Okay.
So there's an instant of time at which every point in space is singular.
Okay, one more question. Yeah.
So it looks like from all the data sets you showed, all of the three models for dark energy predict more or less the same sort of thing. Besides getting more data or finding ways to combine these measurements, is there some potential experiment that could distinguish these different models?
Yeah. So so if you just go back and look at how this guy behaves, so there's you can see that there's some difference between all these models, but the error bars, these are 2 sigma error bars, they're pretty huge. So what you want to do is you want to shrink these error bars a lot, and you want to fill this in much, much more uniformly and try to go to higher and higher redshift. And there are experiments that are being planned to do this. So the first one that's going to do this is the DESI experiment. That's the dark energy spectroscopic instrument. That's a ground-based experiment. It's going to go on the Mile telescope, and it's going to have a robot that puts fibers at places where you have galaxies, and you probably get maybe 5,000 redshifts every night. And they hope to end up with 30 or 40 million galaxy redshifts and measure baryon acoustic oscillations with really tiny error bars all the way from here to maybe up to about 3. And they hope to do this by the mid-2020s. There are also 2 space-based experiments that are supposed to be launched in the early 2020s. So the first one is the European Space Agency Euclid experiment, which is also going to go for baryon acoustic oscillations and weak gravitational lensing. And the NASA has one, it's called WFIRST, the Wide Field Infrared Space Telescope, and that will also be launched maybe in the mid-2020s. And all those guys should get really tiny error bars over a pretty wide range of redshifts, and hopefully in the next 10 years we'll have data that will rule out at least half of these models. But I don't know.
Okay, see you on.
Just a follow-up question. If at the beginning of the time, okay, everything starts to expand, that means at that time, compared to now, it must be much smaller than the universe we have now.
It's actually infinite then, and it's infinite now, and this is a really difficult thing.
Different type of infinite. If it's always expanding, then this infinity must be
It is, yeah. This infinity is bigger than that infinity, but they're both infinite.
It's not a satisfactory answer. Okay. If something is always expand, like you start from 1 over x, then say you end up. This is the infinity, right? You end up with the 1 over x cubed. That infinity is bigger, higher order infinity.
I mean,
so that means in any case, the previous infinity is smaller than
right, but they're both infinite. But they're both infinite.
But you can compare infinity.
You can compare. You see the expansion. So you can do this locally. You see the distance between 2 points gets bigger and bigger, and you can see this from.
No, that's fine. But my argument is, then to back to time equals 0, that infinity is smaller.
That's right. But it's an infinity.
I mean, you can define infinity as if I shoot a laser out, will ever hit anything. It's no ever get to an end. The answer is no. No matter what direction you do that at.
No, but if it's smaller than when you expand, there's a center. That infinity.
No. There's no center.
Well, every start this thing now. I just want to say one thing to you, C1, that 1 over x and 1 over x cubed is, maybe you can say that 1 over x cubed goes to infinity faster than 1 over x, but you can map one to the other exactly. It's exactly the same kind of infinity. And the same kind of thing here. You have counted infinity and uncounted infinity, and some of them can be mapped to the others and some of them cannot. This kind of infinity can map to any kind of other infinity when the universe expands. Thank you all. Thank you for that.